Before we look at additional graphs, I want to talk about symmetry of polar graphs generally. This will be useful for us when we're deciding what a graph looks like once we know what the shape of the graph is going to be. And in fact, it will help us with the circles that we just looked at a moment ago. There's two types of symmetry that I'm interested in us knowing about, and one is called polar axis symmetry. Look at it first. And you really might remember the polar axis is really the positive x-axis. And so we actually might think of this in terms of, and I might even slip and say x-axis symmetry. Now, to be symmetric about the x-axis means that we have whatever we have above the x-axis, we have something that mirrors it in the below the x-axis. Now, here generally we're not talking about parabolas, but if we think about a parabola that opens downward, then it would be symmetric about the x-axis because the x-axis acts like a mirror, or if we fold it along the x-axis, the two parts would match. Now, of course, we're talking about polar graphs, so let me kind of go about it this way and we'll see what it means, and then we'll look at a particular example. So to be symmetric about the x-axis or the polar axis means that if we have a point above or below, then I'm just showing up above here, if we have a point above the x-axis that we know is on the graph, then there's got to be one matching it identically that is below the x-axis. Okay, matches it identically. That is symmetric to it, opposite of it. Now, if we were looking at this particular point, then would have to be the point. Let's stop and think what this up here says. This angle right here is the theta, and of course this distance is the r value. Okay, that's an R, it looks like an N there. Well, if we're going to be symmetric about the x-axis, then that tells us the point below, this would have to be an angle of negative theta, but this is still the same distance R. Okay, that's still the same distance R. So if the point R comma theta is on the graph, then R comma negative theta would also have to be on the graph. So the way we test this, let's come up with an example there. We'll use the equation, determine if, that's kind of what we're doing. Determine if R equal, we'll say 5 plus 5 times the cosine of theta is symmetric about the polar axis. And remember that really we're thinking x-axis as we say that. Okay. Well, here's what it means then. Assume that the point r comma theta is on the graph of some function, let's say r is equal to f of theta, just for argument's sake. Well, in this case, I guess I already had said 5 plus 5 times cosine theta is what we have. Okay, so that means exactly what we see there. When we put theta into the function, we get an r out. That's what it means for r comma theta to be on the graph. Now, what we want to know then, if that point is on the graph, then that implies we must show must show that r comma theta being on the graph implies r comma negative theta is also on the graph. I'm going to a lot of trouble to show this because it will pay big dividends later on. Okay, so what that means is when we put negative theta into the function, then we would get an r out. Okay, so let's take the 5 plus 5 cosine. Instead of putting theta into the function, we're going to put negative theta. And so what we need to show is that also gives us the same r. That gives us r also. And here's how we go about doing that. We need to rely or remember the identity that the cosine of negative theta is exactly the same as the cosine of theta. And that's just simply an identity. And the cosine of negative theta is equal to the cosine of theta. And we get that simply from what we've seen before. That's particularly if we're thinking of a unit circle and we look at an angle theta. So assume that we're talking about an angle theta right here. Well, the point on the unit circle, let's say, has coordinates a comma b. And of course, the cosine of theta is that first coordinate a. Now, if we look at negative theta, then that's going to put us in this position on the unit circle. And notice this point has coordinates a comma negative b, just by the symmetry of the circle itself. And so since a represents the cosine of theta for the top point, and the bottom point, a represents the cosine of negative theta, then that tells us cosine of theta and cosine of negative theta are equal to each other. So back up here, when we change cosine of negative theta to what it's equal to cosine of theta, well, 5 plus 5 times cosine of theta is equal to the same r that we had before. So this shows symmetry. This proves symmetry about the polar axis. And I'm going to just say about the x-axis. So that tells us whatever this graph looks like, whatever is on top is going to match whatever is on bottom. So for instance, if the graph happened to look like maybe this part of the graph looked up here, we had part of the graph that looked that way, then we'd have to have something matching it, just like that below the x-axis as well. Now, a greater dividend here is, notice this just relied on the fact that cosine of negative theta is the same thing as cosine of theta. So let me make a big point here. Any polar function, any polar graph that involves cosine only will be symmetric about the x-axis. The polar axis. And just recall on our example with circles, remember we had a little earlier, I don't know exactly what it was. Let me look back and see what we were really looking at. I've forgotten already. I know it was r is equal to, what was it, 4 cosine theta? I believe that's what it was. Now see, this function involves only cosine theta. And we discovered when we were doing this, we discovered, oh yes, the A value, recall, was 2, because this is a 2 times 2 cosine theta. And because the A value was 2, we decided that this is where 2 is, we decided that the center of the circle is at the point 2 comma 0. And we decided that the radius was also 2. And so we ended up with a circle. I'm just sketching this back in, but just to recall, we ended up with this circle. Well, notice this circle is, in fact, symmetric about that x-axis, isn't it? Half of this graph is above the x-axis and half of the graph is below, and they're symmetric, or they match on either side. They're opposite. And that had to do with what we just shown, because this function had only cosine of theta in it and no sine of theta, or no tangent or no cotangent or any of that. And that's an important observation for us. Well, we'll continue this. The other type of symmetry that I want you to be familiar with is called theta equal pi over 2 symmetry. Well, what this refers to, look real quickly, what this refers to is if we look at the angle pi over 2, that's this angle right here, isn't it? So that's the angle where we're going straight up. That's the angle there. Well, then what we're really talking about here, maybe it would be more descriptive if we said y-axis symmetry. And when we're talking about only polar equations, we really would plot that on a polar axis, and so we don't really have an x-axis and y-axis, but we're overlaying on ours onto an xy axis, aren't we? So when we talk here, we're talking about more or less y-axis symmetry. So back to the idea, if we were looking at a parabola, and in this case a parabola that opened up or down, then that parabola, if the vertex is on the y-axis itself, or the y-axis one way or the other, then we're symmetric about that y-axis. That is, if we fold it on the y-axis, the two sides match, or the y-axis is acting as a mirror image on either side. So let's, as we did before, let's look more generally about what this would mean. If we had a point, let's say that's on this side of the y-axis, and that point has the coordinates r comma theta. Well, that would mean, here's the angle theta, and of course this is the distance r. Okay? That's the distance r. Now, if we're symmetric about the y-axis, it means for every point on this side of the y-axis, there's got to be a matching point on the other side. So we'd have a point right there. Now, this distance right here would be the same value r. Okay, so that r value would be the same. It's the same distance from the pole. But what is the angle theta? Well, the angle theta is actually the angle for this point is pi minus theta. You can think of, here's the angle theta, and if we take the angle pi and subtract theta from it, the angle pi is clear out here, isn't it? And we subtract theta from it, so that means we would go that direction, wouldn't we? Then we're at the particular angle we're talking about. So the coordinates of this symmetric point would have the same r value, but we would have a pi minus theta angle. So to show that a graph is symmetric about the y-axis, it means if we know a point of r comma theta, here's what it means, that if we put the angle theta into the function, we get the same value as if we put the angle pi minus theta into the function. So here what we're going to do is show r equals 5 plus 5 times sine of theta is symmetric about the y-axis. Now that's being not quite accurate. Remember, this isn't really the y-axis, it's theta equal pi over 2. But we're going to call it the y-axis. Okay, so here's what that means again. That means if we instead put the angle pi minus theta in, then we'll get exactly the same r as, excuse me, that was a 5 out here. If we put the angle pi minus theta in, and we put the angle theta in, we get the same value r in each case. In other words, we would have both of those points. And so we're going to go through and see if this gives us exactly the same thing, that is r plus 5 times sine of theta, which is equal to r. 5 plus 5 times theta. I think I bungled up what I was trying to say. But here we have to do a little bit more work. And we have to rely, let me come way over here. We'll come right here. We have to rely on old trig identity. And that trig identity is what we call a difference formula for the sine function. The sine of a minus b. Remember that formula? Well, it says the sine of the first angle times the cosine of the second angle minus the sine of the second angle times the cosine of the first angle. I'll run out of space there. So that's the identity that we need to use because we have the sine of pi minus theta there. So as we apply this identity, let me make sure I have enough room this time. Sine of pi minus theta, according to this formula, would be the sine of pi times the cosine of theta. And then it would be minus the sine of theta times the cosine of pi. I'm sorry that I've got that so scrunched up. So let me bring this over. Well, the sine of pi is 0, isn't it? So here we have a 0 times the cosine of theta. And the sine of theta, next, minus the sine of theta, but the cosine of pi is a negative 1. So we end up having a 0 minus the sine of theta times a negative 1, which of course is just simply positive sine of theta. So what this tells us, of course, is sine of pi minus theta is exactly the same as sine of theta. So back up here, we can rewrite this equation, if you will, 5 plus 5 times sine of theta. And 5 plus 5 sine of theta is just r, so that it tells us whether we put theta in for the angle or pi minus theta in for the angle, we get the same r value out, which tells us that we have symmetry. Now, let's go back and maybe this is, well, let's go back now and see what this tells us. Here's kind of the bottom line in this case. The only thing that was of importance here is we had sine of theta being the only function that occurred, the only trig function that occurred in this polar equation. And so here's our conclusion. Any polar graph that involves the cosine, excuse me, the sine function only will be symmetric about the y-axis. That's important for us to know. Okay. Any function that involves only cosine symmetric about the x-axis. Any polar function that involves only cosine, sine, will be symmetric about the y-axis. That's a big deal. Let's go back and think of our circles now. Recall that we had a polar equation that was r is equal to, what was it, -7 times sine of theta. And here's what we decide. Notice this function only includes sine of theta. So the graph of it I'm expecting to be symmetric about the y-axis. That's the way we're led into this. Now you remember also that we decided in this case, see, we were writing it in the form of r is equal to 2a. And so we said, oh, this is 2 times -7 over 2. That's not quite the way we did it. But yes, and so our a value is the -7/2, or our b value, excuse me, it was a b value here. And so that told us that the radius of the circle, we recognized that it was a circle, and it told us the radius of the circle was the absolute value of -7/2. So the radius was +7/2, 3.5, okay? And then we said, oh, okay, because we interpreted how we're going to recognize this as a circle and also where the center is, well, here we knew that the center, we determined the center would be 0, a, so that's 0, -7/2. Now, I'm just going over that quickly so we can remember what our circle looked like. So, we had a center at 0, -7/2, so let's just assume that's right here, okay? And the radius was 7/2. Well, from here to here is 7/2, and so, and this is the center, and so we ended up having a circle, and it's not a very pretty circle that I'm drawing here, but we had a circle that looks something like that. Now notice, this circle is split by the y-axis. This is in fact symmetric about the y-axis, and that was predictable because the function only had, the polar function only had the sine function, the trig sine function in it, and no other trig function at all. So it was predictable that it would in fact be symmetric about the y-axis. Okay, well, these two pieces are important in the rest of what we do in recognizing these graphs, or most of what we do. The next classification of polar graphs that we're going to discuss are called cardioids. Cardioids will be of one of several forms. R is equal to a either plus or minus, not both, plus or minus a times cosine of theta, or it could be r is equal to b, either a plus or a minus, b sine theta. So examples would be, of course, r is equal to 5 plus 5 times cosine theta, or sine theta. Or we could have r is equal to 5 minus 5 times sine theta. Or we could have r is equal to 3 plus 3 times cosine theta. Or r is equal to 3 minus 3 times cosine theta. Occasionally is disguised a bit, and we might have something that look like r is equal to 4 times 1 plus sine theta. So it may be disguised a little bit, but of course if we multiply that out, that would be a 4 plus 4 sine theta. The issue is we have a constant plus the same constant times either sine or cosine, or a constant minus the same constant times either a sine or a cosine. And of course, this type of graph gets its name because it's vaguely in the shape of a heart. As a cardioid, that makes sense. It's vaguely has some shape of a heart that we would recognize, vaguely the shape of a heart. Not a pointed heart like a Valentine's heart, more like a heart that's actually in us. And another thing to know here is these graphs always contain the origin. As they always, the origin is one of the points that's on the graph. And we'll keep that in mind because there are other graphs that look similar to it that do not contain the origin. Well, I guess what I would like to do is take one particular example and maybe plot a few points for it, and then we'll kind of look at the bigger picture and be able to sketch each one of those above fairly rapidly. So let's take let's take the first one we have up there. R is equal to 5 plus 5 times the sine of theta. Now, one of the things that I'm noticing right away, because it has sine of theta in it only, that this graph will be symmetric about the y-axis. Symmetric about the y-axis. That's a good observation to make. Okay. Now, I'm just going to plot a few points, and I'm assuming we're going to make the assumption that we understand this is vaguely heart-shaped. That should have come from dealing with polar equations earlier. So we'll plot some points. Suppose we let theta be equal to 0 here. Well, if theta is equal to 0, then r would be 5 plus 5 times sine of 0. And sine of 0 is 0, so r will be 5. Now that brings up something very important for us right away, too. The biggest sine of theta can ever be is 1. So the biggest r is ever going to be is 5 plus 5 times 1, or 10. And the smallest sine of theta can ever be is negative 1. So the smallest r value we're ever going to have is 5 plus 5 times negative 1, which is 5 minus 5, or 0. Okay, just keeping that in mind. Now let's let theta be equal to pi over 2. Okay, if theta is equal to pi over 2, of course the sine of pi over 2 is 1, and so r is actually equal to 5 plus 5 times 1, or 10. Okay, that's the biggest r will ever be. So when pi over 2 is the biggest r will ever be. Let's let theta be equal to, say, how about pi next? Well, the sine of pi is 0, so r is 5 plus 5 times 0, which is, of course, just 5 once again. Now I'm going to change up a little bit here, and let's let pi be, theta be, let's say, I don't know. How about see if I can think of a good example. Let's let pi be, let's say 5 pi over 4, just to mix things up a bit. And sine of 5 pi over 4 is negative square root of 2 over 2. We multiply that by 5. We get roughly negative 3.5. Add 5 to that. We get roughly 1.5, roughly 3 halves. Okay, but approximately, and it's only approximate, 1.5. let's let theta be 3 pi over 2. And when theta is 3 pi over 2, then the sine of 3 pi over 2 is negative 1. So we have 5 plus 5 times negative 1, which is 5 minus 5, or r is actually 0. Oh, okay. And let's jump ahead and let theta be 2 pi. Well, when theta is 2 pi, of course, once again, sine of 2 pi is 0. So we have r is 5 plus 5 times 0, or r is just 5. Now, let me draw the coordinate axis, and we'll start plotting these points. And one thing to remember is, although we're overlaying this on top of a rectangular coordinate system, we measure r units. So let's not get these really convinced or mixed up with x and y values. In other words, let's not think that 10 up there is a y value of 10, although it might correspond to that. It's more likely going to correspond to an r value of 10. So let's plot these points. Now, in the first point, 5, 0, remember the angle theta is 0, which means we're going completely horizontal to the right. See, we're going out this direction. And so we measure 5 units in that direction, and that gives us this point right here. And then when theta is pi over 2, well, that's the angle that goes directly up, isn't it? That's the angle that's going all the way up here to the top like this and continue going that way. And so we're supposed to measure 10 units in that direction. And so I've got that up here. Okay, well, that's 10 units in that direction. Now, when we go to where theta is pi, then that is an angle that opens up completely horizontally. That is, we're going to the right horizontally. And we're supposed to measure 5 units in that direction. Well, here's 5 units away from that pole, so that puts us at this position. See, I didn't write that as a negative 5 because that's not representing a y, actually. That's a r value of 5 in that direction. Okay, let's say we have the angle 5 pi over 4, and that's roughly an angle that looks like this. Okay, and that's roughly this angle. And in that case, our r value is 1.5. So we measure along that direction 1.5 units. And that's roughly about right here. Okay, roughly about right there. And if we let theta be 3 pi over 2, of course, that's going directly down, isn't it? That's this direction. But our r value is 0, so we don't move from the pole at all, and so that means we're actually at that position right there. And then if we let theta be 2 pi, well, now we've made one revolution, so we're back to this horizontal angle. We've gone all the way around, and our r value is 5, and so we go back and measure 5 units in that direction, and we're right back to the very first point we plotted. Now, that's not very much information, is it? So it's going to be kind of difficult for us to decide what this graph looks like. I suppose we could throw in a few more points, and I'm just kind of, if we threw in a few more points, for instance, if we let theta be pi over 6, okay, then the sine of pi over 6, I believe, is 1/2, isn't it? Sine of pi over 6 is 1/2. Have to stop and think about that. Yes, the sine of pi over 6 is 1/2. And so r is 5 plus 5 times 1/2, or that's 5 plus 2.5, or 7.5. So we get an r value that's 7.5. Well, now pi over 6 would be an angle that's roughly like this, just roughly. And if we're to measure 7.5 units in that direction, let's see, here would be 2, here would be 4, here would be 6. about right here would be 7.5. So it would be about at that point. And then we could try pi over 6, rather than pi over 6, we could say try pi over 3. Well, if theta is pi over 3, then the sine of pi over 3 is actually the square root of 3 over 2. Oh, we're going to have to calculate here for a moment. Well, if we do all of our calculations, we get roughly 9.5, just approximately 9.5. Well, now, pi over 3, of course, is an angle that's roughly like this, isn't it? And so we measure out in that direction 9.5 units, or approximately. Well, let's see, here's 2, 4, 6, 8. 9.5 would be roughly right there. Now, because of symmetry, here's what we're going to see. Let's connect these points, and we started at this point right here, and then we would move to this point, and then we would move to this point, and then we would move to this point. Now remember, we're symmetric about the y-axis. So over here we have something very similar to this. And you're just going to have to excuse my graphing or my drawing here, but we're going to have something that's going to look roughly like that on this side, okay? Now, we don't have very many more points to work with to understand, but from this point we move to the point right here. So we're doing something like this, but we also next move to the origin, okay? That was when r was 0. And remember, we're symmetric about the y-axis, and so we'll also start up, although I didn't show any more points there, we'll have something that looks roughly like that. Now you can see that looks something like an upside-down heart, hence the name cardioid. Now, I'd like you to notice a couple of things. First, we're symmetric about the y-axis. Okay, that's a critical part. And we see that this is upside down, and if I would put it this way, the most of the heart is above, okay, is above the x-axis here. And that's predictable because we have 5 plus 5 sine of theta. The reason I say that's predictable is because when theta is pi over 2, we'll have our largest value of r, our largest value of r. Now, if we would have had a 5 minus 5 sine theta, then the largest r value would be is when sine of theta gives us a negative 1, because then we'd have a 5 minus a 5 times negative 1, which would end up being 5 plus 5, or 10. So we would have had a different situation there. So this plus is actually giving us a little more information. We'll see later on that most of the graph is above the x-axis, and so we could have anticipated it would look this way. Okay, well, what I want to do next, and we're not going to plot points for the rest of these. Okay, what we're going to do is we're going to use these thoughts to see and compare what we've got in these functions A, B, C, and D as we graph those. And so I'm going to set up the next page. Well, I started to say that I've reproduced the graph from the previous page on this page, but you can see that my graph isn't so pretty, and I apologize for that. And in the future, I'm probably not going to apologize because I'm doing these more or less freehand. Obviously, this should be a little more plump right here, shouldn't it? And it should be symmetric, but it's supposed to be illustrated as symmetric. Okay, let's look at B, and let's also graph B, but let's do this without plotting points. So B was what? R is equal to 5 minus 5 times sine of theta. And I say not plotting points. Let me let me draw some kind of axis here for us to get started. But the notes that I'm going to make here, okay, the notes that I'm going to make is one, the symmetry that I'm understanding here is, once more, it's y-axis, isn't it? We have y-axis symmetry. Okay, so that's an important note. Another important note is maybe what's the first point that we would have on our graph? Well, that would be when theta is equal to 0. We would think of that as the first point. And in this case, if that's true, then, when theta is equal to 0, we still get an R value of 5. Now, I'm not trying to go through all of these R values, or these points, but I'm at least trying to get a good start on what I think is going to happen next. Okay, so let me, like I said, let me draw a coordinate axis here. Okay, here's where I am. I know the biggest R can be is 10 units. And the reason I know that is because the biggest R can be will be when sine of theta is -1. And since sine of theta can't ever be smaller than -1, well, we have a -5 times that -1, which ends up being a +5. So the biggest R can be is 5 plus 5, or 10. Okay. Now the question is, which direction is that 10 going to be? Well, I'm already deciding that this is symmetric about the y-axis, and if I'm going to have a heart that's symmetric about the y-axis, it's got to be vertical. If I turn that heart sideways, like we see on the left, if I turn that heart sideways, then it's going to be symmetric about the x-axis. It's not going to be symmetric about the y-axis. So I'm thinking that this biggest R value is going to be up as high as 10 or down as low as 10 on the bottom side. So I said I wasn't going to plot points, but I think I will look at some representatives. Now, I might be able to do this in my head, but I already decided if theta was equal to 0, my R would be 5. And so that's the point that we had a while ago right there. And next, probably what I would look at is that, well, what would R be if theta was pi over 2? Well, if theta is pi over 2, remember, the sine of pi over 2 is 1. And so we would have R as 5 minus 5 times 1, or just 5 minus 5. And so in this case, R is actually 0. So when we're looking at going straight up, our R value is actually 0, so we don't move from that position. And so that means right away what we're doing, we're moving some, but we're going from this point to this point, and so we're kind of getting the idea already, I've made that a little too big, but already that maybe this heart is upside down, okay, or right side up actually, instead of upside down. Now if I let theta be equal to pi, well that would mean we're going to the left, wouldn't it? If theta is equal to pi, well, sine of pi is still 0, so R is 5 minus 0, which is just a 5. So that means we go to this position, we go 5 units in that direction, so we're at this point. Now remember, we have symmetry about the y-axis, and so we're going to have something that looks very much the same over here, okay? Much like that. And then we could say, well, let's let theta be 3 pi over 2. Where am I doing? I'm going to the left, I'm going up, I'm going to the right, I'm going up, I'm going to the left, I'm going down. Well, the angle 3 pi over 2 puts us at this axis, doesn't it? Okay, well, the sine of 3 pi over 2 is -1, so R is 5 minus 5 times -1, or R is our 10. So now we see that the biggest value of R is when we're going downward. And so we mark off 10 units in the direction that is down. That puts us at this position. Now, since we already know it's a cardioid, then we can get the idea the way this is going to look as we fill in. It's going to look like this, isn't it? Okay? And that was pretty easy for us to sketch without a great deal of trouble. Now, that's not perfect. It's a little more round than that, actually, but it gives us a quick sketch. Okay. let's move our attention then to the example C, and that was r is equal to 3 plus 3 cosine theta. So here my notes go this way. I guess I ought to put up some kind of axis, but notice that the biggest r can be is going to be a 6, and the smallest r can be is when we have a negative cosine value. And the smallest cosine can be is negative 1, and so the smallest r is going to be is 3 plus 3 times negative 1, or 0. So I'm going to set up, I don't need quite as big of coordinate axis as I had before. Now, before I go much further, let's go back up to the two examples above. We can start predicting where does most of this graph lie. You know, above we see that most of the graph was above the x-axis, and on B most of the graph was below the x-axis. Well, that's where it had to do with where r was the biggest value, and of course r is going to be the biggest value when we basically have a sign value that's positive because of that plus here. In this case, r is going to be the biggest value when the sign has a negative value because we've got to offset the minus sign that we have there. And so when we have an angle that is going down is when we would expect the biggest r value there. And it's almost like if we have that plus, most of the graph is above the x-axis. If we have that 5 minus 5, most of the graph is below the x-axis. Well, here, let's see if we can predict the same thing. Except in this case, our symmetry, you know, we have x-axis symmetry here because we're dealing with cosine. So we have x-axis symmetry. So that means it's got to be laying down, okay? And here, because of that plus sign, I'm predicting most of the graph is going to be on the positive side of the x-axis. That's right of the y-axis. That's what I'm predicting. So if I was trying to scale what I've got here, I might put more of my axis over here on the right-hand side, okay? And I'm going to actually think that the most of this graph being on that side, the biggest r is going to be is 3 plus 3 or 6, and so I'm going to mark off 6 units right away here, okay? Now, I'm guessing because we're symmetric about the x-axis, this is laying on its side, and most of the graph is going to be on the positive side of the x-axis. Like above, most of the graph was on the positive side of the y-axis when we had a plus. So I'm expecting these other numbers that are vertical are going to be the 3 like we had the 5s above, because anytime I have a cosine value that's 0, then my r value will be 3. And I'm expecting that to happen when theta is pi over 2 or when theta is 3 pi over 2. So right there's my 3 and right there's my 3. That is going in those directions. Now, let's kind of verify what I've said in words with a few points. In this case, if theta is equal to 0, the cosine of 0 is 1, so r is 3 plus 3 times 1, or r is 6. So remember, our angle is 0. Don't get confused with that. Our angle is 0, so that means we're going to the right. And so we move 6 units to the right from the pole. That puts us at that point. Remember, we got polar points, not rectangular points. Now when I choose for theta to be pi over 2, that means we have an angle that's putting us in a vertical position, upward. And in that case, cosine is 0, so I have r is 3 plus 3 times 0, or r is 3. So if I go up 3 units for my r value, then that puts us at this position. Now if I let theta be pi, we'll look above. If theta is pi, cosine of pi is negative 1. So r is 3 minus 3, or 0. Well, now when theta is pi, that means we're going in this direction, doesn't it, to the left. And we're starting at the pole to measure the distance of r, but since r is 0, we never move from that pole. Okay? Well, now we can already start guessing what's going to happen, okay, because we're symmetric with the x-axis. But let's go ahead and choose theta to be 3 pi over 2. Well, when theta is 3 pi over 2, once again, cosine is 0. And so r is 3 plus 0, or simply 3. So now at 3 pi over 2, that is, we're going in a downward direction, and our r value is 3, so we measure 3 units in that direction. So we real quickly then can anticipate that this graph is going to look like this heart. Oops. Okay, well, I'm sorry that it should be more round than I've got it instead of more oblong like that. But here we have our cardioid. And once again, it's the biggest part of it is to the right, the positive side of the x-axis because of that plus 3. And the furthest it's going to be along that x-axis is that 3 plus 3. Vertically, the highest it's going to be is 3, and the lowest it's going to be is 3. Or maybe that's not completely accurate, but those are the intercepts, if you will. Okay? Lastly, we're going to go through this next one more rapidly, and that's y is equal to 3 minus 3 times cosine of theta. This time, what we're going to anticipate, and we will be correct, I'm going to just sketch this in, not be quite so precise here. I'm expecting most of the graph, okay, symmetric about the x-axis, okay? So I'm expecting this to be a cardioid. It's going to be lying down, and so I'm doing a quick check and saying, oh, okay, if theta were its x-axis symmetric, okay, and I'm thinking in my head to get a starting point, but I'm going to write it down, but I'm thinking in my head, well, if theta is 0, we're talking about this angle to the right. And if theta is 0, then what we have for r is 3 minus 3 times 1, or 0. So when we're thinking of this angle to the right, our r value is 0, so we never move the pole. Okay, so we're actually starting at the dimple of the heart, aren't we? Of the cardioid. R is also 0, but that's a distance, and the theta 0 is actually an angle. And then if I went to pi over 2 for my r value, excuse me, my theta value, well, their cosine is 0, and we get an r of 3, and that's this position right there. That's where 3 is, okay? So I'm already getting the idea that this cardioid is doing this, okay? Now, when, 3, pardon me, when we have an theta value of pi, then cosine of pi is -1. So we have 3 minus 3 times -1, or actually 3 plus 3, or 6. So it's when we're talking about this angle to the left that we get our biggest r value, which is 6. So we are putting that point in. And now we already have the idea of the symmetry, so we understand that our graph is going to look, see if I can do this one a little better. Whoops. And then it comes over here and it picks up this point. Remember, this is at 3 also, but 3 in a downward position. And then we come back to here. So, again, I apologize for the ugliness or the inaccurate part of my sketches, but you get the idea, I hope. So looking at the function, and again, because this minus, and we know we're symmetric about the x-axis, then most of this graph is on the negative side of the x-axis. Okay, predictable, predictable, predictable. So we're going to change